So here we have few problems. The rotational constant of entry is 2 centimeter inverse. The wave number of the incident radiation in the Raman spectrometer is 20487. What is the wave number of the first scattered Stokes lines of 14 nitrogen? And next problem we have a 24491 centimeter laser line was used to excite a O16 molecule to obtain the rotational Raman spectrum. The resulting rotational Raman spectrum of O2 molecule has first Stokes lines at this one. So we have to identify the B value here, and here we have to identify the first scattered Stokes lines where it is coming. So we'll see these two problems, and also I have many other problems also. So this is 0. We have principal 4j plus 6b. So 0 will be, this is 6b, and this will be 10b, and like that 4 into this is 0, 2 plus 6, 4 2s are 12, 12 plus 6 18b, 4 2s are 4 2s are 8 is 14b, 4 3s are 12 plus 6 18b. So like this, 6b, 10b, 14b and 18b. So this is the diagram. The question what he asked is the rotational constant of N2 is 2 centimeter inverse. So B value is 2 centimeter. The wave number of incident radiation in a Raman spectrum is 20487 centimeter inverse. So what is the wave number of first scattered Stokes lines? Stokes lines means this one, right? First scattered Stokes line is this one. First scattered Stokes line is this one, okay? Scattered means from here. So the energy difference between these two is 6b. So we know the B value, that is 2. 6 into 2 equals to 12 centimeter inverse. So now the wave number will be, the scattered wave number is equals to incident radiation minus 12. So how much incident radiation here? 20487 minus 12. So this will comes out to be 7 minus 5, 7 minus 2, 5. This will be 7402. So this much we'll get. So this is the answer. So you have to calculate this way. And the next interesting question, this is very important and interesting. So a 20,491 centimeter inverse laser line was used to excite O16 molecules to obtain the rotational Raman spectra. The resulting rotational Raman spectrum of O2 molecule has first Stokes line at 20479. The rotational constant. So here we calculate the rotational constant. We calculated the wave number by using incident radiation and the rotational constant. So what he is asking here in the second problem, they are asking us to calculate the rotational constant, and the next rotational Stokes lines is expected at. So when we have a oxygen 16 isotope, here the spin value is equals to 0. So when the spin value equals to 0 in the rotational Raman spectroscopy, all even number lines will disappears. So what are the even number lines? This is the 0, this is the 1, 2, 3. Okay, this 0 disappears, this 2 disappears, like that. So the spectrum is looks like this. The starting will be this one, 10b. The next line will be 18b. The next line will be 5. How much 5? 4, 5 plus 6, 26b. 4 5s are 20 plus 6, 20b, 26, like that. It's 10b, 18b, 26b. Okay, so this is a 1, this is 3, this is 5. So here 0 is missing, 2 is missing, 4 is missing, or even numbers will be missing in this case. Okay, So this diagram is for this. So now we have to calculate the rotational constants. So how you will calculate the rotational constant? Take incident radiation minus wave number, so you will get this value. So what are the incident? So 20497 minus 20479, so you will get the rotational constant is around this will be 12. Okay, right? 11 minus 9 is 2, 6 minus 12, it will come 12. Now what is the energy difference? We have to identify this is the B value, because this gap is this one, this is 10B equals to 12 centimeter inverse, because the energy difference, see, this energy difference is 10B, right? So now B will be 12 by 10, it comes approximately 1.2 centimeter inverse. So this is the B value. So when we have a J value, I value is 0, in that case all even numbers are missing. Now here the energy difference between the first Stokes lines and this daylight line is 6B, but when we have a spin value 0, in that case it will be 10B. And the second question is, the next rotational Stokes lines is expected at. Next rotational Stokes lines means 18B. So that means what is the energy difference here? This here the energy difference is 8B, right? So B value how much? We already calculated B value is 1.2. So this will be 8 into 1.2. This comes out to be around 16, 8 1 8, 9.6. Okay. Now the second Stokes line appears at, we have to take this sorry, not this one, because first Stokes lines came here, the second Stokes lines has to be means we have to, means like this is for we can say incident radiation. This we can use only for the to calculate the first Stokes lines. For second Stokes lines means whatever means you have to take this one, because the first Stokes lines appearing at this. So from this we have to take second Stokes lines, means from here we have to subtract this rotation constant, then we will get a second Stokes shape line. So 9.6, it comes out to be, let me do in calculator, yeah, 20, few examples: H2, HCl, CO, CH3Cl, H2O, here the state is liquid state, NH3, NH4Cl, and this is the solid. So the question is, among all these compound, which compound shows pure rotational spectrum, or we can also say that pure microwave spectrum, because rotational is nothing but microwave spectroscopy. Okay. So what is the first condition to be a molecule to be active in the pure rotational spectrum? That is a permanent dipole moment. The molecule should have a permanent dipole moment. So out of these compounds, almost except H2, remaining all compounds will be having a permanent dipole moment. Okay. Now, so another condition which we have for a pure rotational spectrum is the compound should be in the vapor state. So the liquids and gases can't show, sorry, liquids and solids can't show the pure rotational spectrum. Okay, only vapor compounds can show the pure rotational spectrum. So from this point we can remove H2, and from this point we can remove water and ammonium chloride. Okay, remaining HCl, CO, CH3Cl and NH3, these are the gases and they shows the permanent dipole moment. So because of that reason, these four compounds are active in the pure rotational spectrum and they shows the pure rotation spectrum. So this is the one question. And the second question we have CO, CH4, CH3Cl, water, ammonia, C2H6 and SF6. So these are the compounds. The question is, which molecule shows vibrational Raman spectrum? Vibrational Raman spectrum. So now first we see about the I think we talk both vibrational Raman spectrum as well as rotational Raman spectrum. Rotational Raman spectrum. So first I talk about the rotational Raman spectrum, then I go for the vibrational Raman spectrum. So the condition for the rotational Raman spectrum is there should be some permanent dipole moment in the molecule, which are the molecule they have given. Thus there should be some permanent dipole moment, then only that molecule can be active in the rotational Raman spectroscopy. So out of these compounds, methane and SF6, so these two belongs to the spherical tops. So in a microwave spectroscopy we have linear top and spherical, symmetric, asymmetric. So out of these four tops, this spherical tops shows dipole moment is 0. Means like they will not show permanent dipole moment. We can say that no permanent dipole moment. So because of that reason, these two molecules are inactive in the rotational Raman spectroscopy. But when we, so remaining all these compounds are active in the rotational Raman spectroscopy. CO, chloroform, water, NH3, C2H6, they are active in the rotational Raman spectroscopy. Okay, and when we are talking about a vibrational Raman spectroscopy, all these molecules are active in the vibrational Raman spectroscopy, because when we take a methane, so what is the vibration? Vibration means we can stretch this bond like this. So when we stretch this way, and there will be some dipole moment, we can produce by stretching this bond. Okay, for vibration Raman spectrum, there should be some minimum change in the dipole moment. Permanent dipole moment here it's not required. Permanent dipole moment condition is not required here. So minimum change in a dipole moment, if we can produce a minimum change in the dipole moment, that produces the vibration Raman spectroscopy. Okay, so what we need to remember here, so out of all these spherical top molecules, out of all these molecules, spherical top molecules are inactive in the rotational Raman spectrum, because they do not have a permanent dipole moment. But when you are talking about vibration Raman spectrum, all these compounds are active, because when we are stretching this bond, that time we can produce some little bit dipole moment. And all the compounds which are having a V shape, they are active in the microwave. And then linear molecules, when we have a linear molecules, that way linear molecules which are having a this kind of molecules, these are inactive in microwave, because there is no we cannot produce any dipole moment here. But linear heterocyclic hetero atom containing linears are microwave active. And then so these are the some examples we have. And then next question, or the stretching modes of diatomic O2 and N2 are IR active? This is the question. Okay, so O2 N2. So for dipole, for IR we should have some change in the dipole moment, right? So one general point, just remember here, all diatomic molecules are active in Raman spectra and inactive in IR spectra. So this is because of, as we know that by stretching this bond, this oxygen this way and this oxygen this way, we can create some change in the polarizability here. The main criteria which on basis of which we say the given compound is Raman active or not, the main thing is the polarizability, right? So upon stretching these bonds like this, so we can produce some polarizability. So because of that reason, all diatomic molecules are we can produce some polarizability change, so that's why those are Raman active. And next question, how many degree of freedoms are possible for BF3 molecule? Okay, so we have two kinds of principles here. When they ask degree of freedom, the principle is 3n only. So when they ask vibrational degree of freedom, so that time we have a 3n minus 6 and 3n minus 5. So if they ask simply degree of freedoms, we have only 3n. So n means the number of atoms. So here we have 4 atoms, 3 into 4. So total 12 degree of freedoms are possible for this compound. And when we are talking about vibration degree of freedom, so as we know that BF3 is a non-linear molecule, so we can consider as 3n minus 6. So this will be 3 into 4 minus 6. So total 6 vibration degree of freedoms are possible. Okay. Now out of these, how many are IR active? How many are Raman active? Okay. So it's all depends upon like if it is a stretching vibration, here total 3 symmetric stretchings we have, and 3 bendings we have. Okay, so out of 3, like if it is symmetric, so that will be Raman active and IR inactive. Then we have CO2 molecule. So we have one stretching, symmetric stretching, one asymmetric, and 2 bendings. So this is Raman active, these 2 are IR active. So total we have 2 IR active modes and 1 Raman active modes. And the next question is a simple question, like what is the HNMR spectra of HD compound? Okay, so here the hydrogen couples with this deuterium, so 2 into 1 plus 1 will get a triplet with a 1:1 ratio. And when you are talking about deuterium NMR, so in this case the deuterium couples with this hydrogen, so now it will be a doublet. And then we talk about the NH4 plus compound. For this, if we record 1H and 15 NNMR, okay, in proton NMR it couples with the nitrogen. So that nitrogen here is having a spin of, so 15 isotope is having spin of 1, 2 into 1 plus 1, this will be the triplet 3. But what about intensity? 1 is to 2 is to 1 or 1 is to 1 is to 1? So whatever that this Pascal diagram we have, this Pascal diagram is only applicable for the spin which is having a 1 by 2. The compounds which are having a spin 1, for that this diagram we have like this: 1 is to 1, and here 2 1. So for triplet we have 1 is to 2 is to 1. So this diagram is not applicable for the molecule atoms which are having a spin of 1. Okay, so molecules which are having spin of 1, for them this is means this is applicable. Okay, so when we record 1H NMR for NH4 plus compound, so we'll get a peaks of 1 is to 1 is to 1 ratio. And when you go for the 15 N NMR, so in that case the nitrogen couples with 4 hydrogens, will get a 5 length signal. So here the intensity will be this intensity only. This will be 3 3 1. This is for quadrate. 1 1 1 3 or 4, 3 3 or 6, then 3 1s are 4. So this is the intensity. So 1 is to 4 is to 6 is to 4 is to 1. And the next question we have, next topic is about the mutual exclusion principle. Mutual exclusion principle. So here we'll talk some of the problems. So the question is whether all bands in SO2 are Raman active or not, and IR active or not. Okay, now so the main point we need to remember here, when you're talking about a mutual exclusion principle, that means there should be a center of inversion. Then only we can talk about the mutual exclusion principle. So according to this mutual exclusion principle, if any band is active in IR spectroscopy, so that band is inactive in the Raman spectroscopy. And if any band is active in a Raman spectroscopy, that is inactive in the IR spectroscopy. Why it's this like this, I will explain later. And now we'll talk about the SO2. So if you want to answer this question, the main thing what you need to be knowing is the shape of this compound. Okay, the shape of SO2 is just like water molecule. This will be like this. So when you are talking about water, so compounds which are having a V shape, so they will be having a permanent dipole moment. And which compounds which are not having a center of inversion, so they will be active in IR spectroscopy as well as Raman spectroscopy. So in this case, in case of water, we don't have a center of inversion. So because of that, all the bands are active in IR spectroscopy as well as Raman spectroscopy. And since the SO2 also having the shape similar to the water molecule, all the bands in SO2 are active in a IR as well as Raman. Okay, so this concept you have to remember it. Okay, so when you talk when they have given some compound which is having a center of inversion, and that time only we can talk about the mutual exclusion principle. Other than center of inversion, if any compound they have given, so those compounds are active in Raman spectroscopy as well as IR spectroscopy.